Okay. So yeah, quick revision before we begin class today, guys. Last week we talked about the most important thing, which is thermal expansion, right? Thermal expansion is essentially the reason why the volume of any solid increases. It is usually because when we supply heat energy to the molecules, what's happening is these solid particles here, they'll have more energy and vibrate in a larger position. Instead of this small position here, they vibrate in a larger position, thus taking up more space and eventually expanding in all directions. Last week, we talked about the applications of thermal expansion, which is usually the high tension cables. If you look outside, you always notice that the high tension cables are slanted. It's because they are taking into consideration on a hot day, the wire is going to slant even more. On a cold day, the wires are going to contract. And if you make the wires too short, what's going to happen is during a very cold day, the wires will actually have tension between each other and eventually contract and break apart, right? So we definitely do not want that. We also talked about the metal railways having gaps in between here. The reason why they have gaps is because the engineers already taken into consideration that the thermal expansion due to the friction from the train is going to cause this railway to expand and eventually, prevent buckling from occurring. And then we also talked about airplanes that have friction with air here. What's going to happen is as they continue flying in the air, a lot of air particles are going to be bombarded onto the plane, which is obviously going to create friction and heat as well. That's why there's always a little bit gaps in between them. Last week, we talked about this phenomena where when we put a thermometer into a hot liquid, we notice that the liquid level drops a little bit before it rises fully. Why does that happen? Again, for those who cannot remember, let's imagine, guys, today here we have a cup of hot water, right? Let's say a cup of hot water, which is at 100 degrees Celsius now. And when we put a thermometer inside, right? Oh my God, a poorly illustrated thermometer, but a thermometer nonetheless, right? What's going to happen is, right, this liquid is inside this glass bulb here, right? When we put the thermometer in the hot water, what's happening is the heat will actually heat up this glass bulb first. And when it heats up this glass bulb here, what usually happens is it will go through expansion and the volume here increases slightly, which causes the liquid level to drop a little bit from its original position. But once the heat penetrates through this glass layer here and starts heating up this liquid, eventually the liquid will start rising to, let's say, 100 degrees Celsius mark here. This is because heat has to penetrate through the glass, meaning to say it expands the glass first, causing the liquid level to drop a little bit before rising towards the top here. You understand what I'm talking about? But let me know if it's going too quick. Oh, guys, by the way, physical classes, we're planning to resume physical classes already. For those who are interested to join back the physical classes, you can come back to the center. I think Chi Hin, maybe your mom would want to send you to the physical classes. What do you think? Would you want to come back to the physical classes, Chi Hin? Hello? Wait, Chi Hin, can you hear me? Hello, Chi Hin, Chi Hin. Wait, did you hear what I say or not? You want to come back to physical classes or not?
My mom allowed that I do.
You ask your mother, then if not, we'll just continue the online classes. It's going to be hybrid anyway. And then Rajdeep, I think you stay nearby as well, right? You can maybe talk to your dad if he wants to send you back to about the physical classes. Just let me know. Okay. Yeah, and then after that, from here, what happens is because the glass is heated first, which causes the bulb to expand. The liquid level drops a little bit before rising towards the top because liquid expands much more than solid, guys. So this is what we talked about last week. We also talked about the calibration and fixed points of a thermometer. You're going to see this word very, very often, guys. Whenever we talk about fixed points are essentially a certain temperature where something for sure happens, right? For example, the melting of ice. Last week, I talked about this, right? If you've ever seen ice melt before, it is because the temperature is for sure at 0 degrees Celsius. Because if you think about it, at -1 degree Celsius, the ice is definitely not going to melt. Means to say it's going to be purely ice. At 1 degree Celsius, the ice would have fully melted into water, so you definitely won't see the ice at all. The only time when ice is melting is when the ice is at 0 degrees Celsius. At that point, you can kind of see like water droplets at the side of the ice cube, right? This for sure is going to be 0 degrees Celsius, which is very commonly used in calibration of a thermometer. So you guys must know this. Now, of course, the next fixed point is obviously the boiling point of water, which for sure is 100 degrees Celsius, right? If you guys ever cooked Maggi mee before, right? If you guys don't have kaka at home and you actually have to cook your own Maggi mee, you'll notice that when the water starts boiling, you can see like water bubbles inside, then you can see steam coming out from the water. At that point, for sure, it's going to be at 100 degrees Celsius, because at 99 degrees Celsius, the water is not going to boil. At 101 degrees Celsius, the water will have fully converted into steam already. So when the water boils, for sure it's going to be 100 degrees Celsius. These two fixed points are always asked in your IGCSEs, right? They will always, especially in paper 2, you know how IGCSEs will scam you guys. They will give you a question with a thermometer here, right? They'll say that this thermometer here, here it can measure negative 10 degrees Celsius, and here it can measure 110 degrees Celsius. Then they'll ask you, what are the fixed points? What are the fixed points of this thermometer here? Now, a lot of students, they try to be funny, and then they tell me, oh, the fixed points is negative 10 degrees Celsius and 110 degrees Celsius. That is definitely not the answer, because this is the range of the thermometer, right? Fixed points for sure, regardless of whatever thermometer they give you, even if it starts off with 40 and 60 degrees Celsius here, your fixed points for sure is going to be 0 and 100 degrees Celsius. Please don't ever lose marks in this, because it is as free marks as it can get already. All right, so everyone, please make sure you know this here. Then last week, before we head off, I kind of talked a little bit about the sensitivity, the range, and the responsiveness, right? But then when I was looking through the notes, I noticed that some of the notes may not have the same page as this. Guys, for those who received my booklet already, is this the same page in your notebook? Anyone has a different page from this? Like the older version of this page? Anyone? Oh, it's the same page? Yeah, then most likely it's the same page for everyone. I was just afraid that I sent out the older version. But yeah, since everyone has this, let's go through these few things again, guys. These are essentially the most important thing in your IGCSEs. For sure, paper 2 at least got 1 or 2 questions talking about this here, and for sure, not for sure, paper 4 occasionally they'll have 1 question talking about sensitivities here, right? So the first thing you want to remember is basically, we talked about this a little bit. We are going to learn about 4 main things here: sensitivity, linearity, responsiveness, and also range of a thermometer. Contrary to many people's belief, whenever I ask the students what does sensitivity mean to them, they always tell me that sensitivity is how fast the thermometer can react, which maybe some of you guys have that as well. I think it's because biology or chemistry, they teach something different for sensitivity. Is that the case? Do you guys take biology? Do you take biology or chemistry? Do you learn sensitivity in biology or chemistry?
Yeah.
Is it a different definition here?
Yeah.
Oh, yeah, most likely that's the reason why. But for physics, right? For physics, oh shit, let me actually close the door. I think it might be disturbing other students with my constant shopping. Like I was saying, guys, whenever we talk about sensitivity in terms of physics here, guys, sensitivity is the ability to measure very small changes of temperature. For example, if I were to compare a ruler versus a micrometer screw gauge, you all know what a micrometer screw gauge is, right? Yeah. Obviously, the micrometer screw gauge can measure much smaller change in length, right? So we can say that the micrometer screw gauge is definitely more sensitive, okay? So whenever we see the word sensitivity, it is just the ability to measure small changes in temperature. Linearity is basically equal spacing between each reading. Last week, I mentioned that in order for us to have equal spacing between each reading, you know, like how a thermometer's reading will be like 0, 1, 2, 3, 4, 5, 6, right? They all have equal spacing between each reading. The only way we can label it with equal spacing is by using linearly expanding liquids, guys. And last week, I talked about this. Linearly expanding liquids is basically alcohol and mercury, right? You can see that thermometers always are silver or red in color because it is definitely the liquid inside is definitely going to be alcohol or mercury. These liquids are assumed to be linearly expanding, meaning to say every 1 degree Celsius change leads to like maybe 1 cm change of the expansion. That's why like 2 degrees Celsius will be 2 cm, 3 degrees Celsius will be 3 cm here. This is what we call linearly expanding liquids. For non-linearly expanding liquids, like for example, one day if you try to be funny, you put apple juice or orange juice or even your own saliva into the thermometer, you know for a fact it doesn't work, right? Because the scale will be damn off, right? Like maybe it will be like 0, then 1, then 2, then like 3 here. You can obviously see that these are non-equal spacing readings, right? So that's the reason why thermometers are always 2 colors, are either silver or they are red in color, because they are linearly expanding liquids. And thus, obviously, they should have equal spacing between the readings. Now, responsiveness is basically what you learn in biology, how fast, right? Responsiveness is basically how fast you can react on. Usually, for thermometers, we wouldn't say that it's very responsive because the heat has to penetrate through the glass layer before it reaches the liquid, right? Later on, you're going to learn something about something known as a thermocouple. I think I mentioned this last week, right? Thermocouple is essentially a thermometer on steroids, right? You can measure like super large range. You can measure super fast responsiveness because thermocouples here, they use metal to measure the temperature difference instead of thermometers, which use liquid expansion to measure temperature difference. And range is essentially, like the name suggests, the maximum, the difference between the maximum and the minimum reading, right? For example, if I have 0 to 100 degrees Celsius, the range is okay. If I have negative 100 to 200 degrees Celsius, the range is much better. If I have like 10 degrees Celsius to 40 degrees Celsius, I can say that the range is pretty damn shit, right? So that's the difference of range you should know. It's basically just the minimum reading to the maximum reading. That is essentially the range, okay? Now, before I proceed on, anyone's got any questions, especially maybe the new student? Any questions that you don't understand or want to clarify? Good, 100% absorption rate, just the way I like it. If you all have no questions, then let's proceed on to the more important parts here, guys. Now, in your IGCSEs, right, whenever they talk about sensitivity, linearity, range, and responsiveness, usually they'll ask you something along the lines like this. Person A has thermometer X, and this thermometer X has, let's say, bad sensitivity. What do I do to increase the sensitivity of the thermometer? Usually the question will be like, how do I improve the sensitivity? How do I improve the linearity? How do I improve the responsiveness? And how do I improve the range? Now, whenever they talk about all these improvements, first and foremost, if you look at the notes here, right, you have to know what they represent. By definition, sensitivity is the ability to measure small changes in temperature. A small change in temperature leads to a large change in reading. For example, last week I drew this, right? Let's say, for example, right now the difference in temperature is 10 degrees Celsius. Today, obviously, this is going to be better sensitivity, and this is going to be not so good sensitivity, right? It starts from 0 to 10 degrees Celsius here. If today I change 10 degrees Celsius, the reading will be this, because the reading I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The difference, the distance measured is going to be here. But if today I have something that has weaker sensitivity, you'll see that usually the change is much lesser because it starts with 0, 5, then 10 already. Both of these are 10 degree difference, but you can see that this one changes much more, this one changes much less, which boils back down to the to the statement here, guys. A small change in temperature, both 10 degrees Celsius, leads to a large change in reading. This one has this much reading change. This one has this much reading change. Can you guys see the difference here? Right. So one is small change, one is large change. And there are only two known methods to improve the sensitivity of the thermometer. Number one, use a narrower capillary tube. The capillary tube is this thing here, by the way. This thing here is known as the capillary tube. Oh, there's a question. Less dense liquid, cross it out, right? Yeah, cross it out. We usually in your mark scheme, I barely see that. That's why I made some adjustments to the notes as well. If you see this word here, less dense liquid, just cross it all out, because I don't recommend writing that as an answer anymore at this point of time. Okay, just everyone just cross it out first. Okay. So yeah, definitely it's yours. Yeah, but don't write down first. I'll pay attention first. I'll give you all time to write down. Yeah. So, like I said here, why is it important that we use a narrower capillary tube? Because imagine this: if we have a narrower capillary tube, the same amount of liquid inside the thermometer needs to travel less, right? Meaning to say it can go up much further. So, if I were to draw a illustrated point here, let's imagine today I have a thermometer that is this thick in terms of its capillary tube, and I have a thermometer that is this thick in terms of the capillary tube. The volume of liquid here is going to be the same. Let's say this one here has 10 meters cubed, which is a damn huge number, which is quite practically impossible. But just for the sake of argument, let's just say that they both have the same amount of volume of liquid here. For a narrower capillary tube, less amount of volume is able to travel up a higher distance. Whereas for a wider capillary tube, the same amount of liquid will only travel this distance here because of the volume it has to expand through, right? So you can imagine that maybe this volume here is 10 meters cubed, and obviously this volume is 10 meters cubed as well. Today, the most important thing, guys, you have to remember this, the best way to improve the sensitivity of a thermometer is always using a narrower capillary tube, so that more liquid can travel up the capillary tube. All right, everyone, this is super important. For sure, come up in your IGCSEs, guys. You have to know this. Have any questions, by the way? All right. So this is the first thing that you want to do to improve the sensitivity. The second one is quite relatable and quite logical as well. You want to use a larger glass bulb here. Why? Because if today you have a larger glass bulb, obviously a larger glass bulb will contain more liquid inside, right? And when there's more liquid inside, yet again, the ultimate goal is to push the liquid as far as possible, right? Because the definition of sensitivity is large difference in the reading, right? We want to push the liquid up as much as possible to increase the sensitivity. Right, so this one here, very, very important. Anyone's got any questions? Two of these are the most common improvements in your mark scheme, guys. Narrower capillary tube and larger glass bulb. Of course, there's a few more, right? Different year, they always have different answers. But these two are the most common, widely known answers in the mark scheme that is definitely acceptable. In fact, in your paper 2, they always say this as well. So, yeah. Just keep this in mind. I'm sure most of you guys will not remember this until you're facing some questions. But just keep this in mind, guys. All right. Then after that, we want to skip directly to the range part here. Why? Because, yeah, larger glass bulb means to say there's going to be more liquid inside, right? So you have more liquid to push up the capillary tube, basically. Right? Nice. All right, so the next thing we want to talk about is basically the range. Why? Because if you remember last week, I mentioned somewhat that range and sensitivity, they are the exact opposite of each other. Meaning to say, today, if I want to increase the sensitivity, the range for sure drops. If I want to increase the range, the sensitivity for sure drops. Now, if we look at the definition here, the range of a thermometer is the difference between the maximum and minimum temperature that the thermometer can read. If you look at the improvements, it is the exact opposite of sensitivity. Number one, increasing the diameter of the capillary tube, which is the exact opposite here, right? And then the second one is decreasing the volume of the bulb, which is the exact opposite here, right, guys? You have to keep this in mind. You can only either improve the sensitivity or you can improve the range. You can never do both at the same time because they are essentially the opposites of each other. Very important. Keep that in mind, guys. All right, sensitivity up, responsiveness for sure down. Responsiveness up, sensitivity for sure down, guys. Very important. All right, then after that, if you can understand that, linearity and responsiveness is quite straightforward at this point. In terms of linearity, to be linear is to have equal spacing between each reading, which is essentially everything that you measure. I've never come across any measuring instrument that has non-linear spacing distances, because that will just be done now, honestly, right? So no one ever does that. And how do we improve the linearity of the thermometer? Is by using linear expanding liquids such as alcohol and mercury. I mean, mercury and alcohol, right? But these two are always used in the thermometer because they are assumed to be linearly expanding liquids. Okay, now responsiveness is the easiest one of them all. Responsiveness is the ability to react fast to temperature change. The only known method to improve the responsiveness is to use a thinner glass bulb. Because like I mentioned just now, right? Just now in this scenario here, if I have a glass bulb, a thick glass bulb, the heat has to penetrate through this layer of glass before it reaches the liquid, right? Today, if I use a thinner glass bulb, right? If I use a thinner glass bulb in the same hot water here, what's going to happen is the heat only needs to penetrate through this little layer of glass before it reaches the liquid here. So all of these things kind of make sense, but you have to do a lot of practice to get it in your head. All right, guys. Anyone's got any questions? Maybe the new student on the floor? Anything else for those who are online? Anyone has any questions from this part here? No, good, 100% absorption rate, just what I like. So if you look at the bottom part of this page here, this is basically the tabulated stuff that you need to know, right? I've gone through the courtesy of making life easy for everyone. Please, later on, when you're doing the questions, for sure you won't be able to remember everything I say, which is obviously a normal phenomena. Please make sure you learn yourself by referring to the table here, guys. If you just look through it real quick, change the thermometer, increasing the size of the bulb is obviously supposed to increase the sensitivity, but it will shorten the range in terms of responsiveness. It will have zero response, right? It won't change now, right? Increasing the diameter of the capillary tube is going to increase the range, but it's going to decrease the sensitivity, essentially what I mentioned. No, not much change here. Increasing the length of the stand will have a longer range, not much change in sensitivity, not much change in responsiveness. Using a thicker glass, obviously no change in sensitivity and range, but it will improve the responsiveness now, right? Sorry, it will improve because I'm increasing the thickness of the glass, right? So it's going to be less responsive. All these are already tabulated to you. Please make sure you refer to it later on. When you're doing the question, you know, like what really grinds my gear is like when, let's say, I see some students that are attempting the questions somewhere along the line, which ask how to improve the sensitivity, and then they'll just like stare blankly into the question. Guys, you're not supposed to stare blankly at the question. The notes are here for a reason. You're supposed to refer to it, get it in your head, and write down the answer with your own wit, right? So just make sure you know how to do that later on. All right. Then, moving on to the final part of this chapter here, which is essentially a thermocouple. Now, thermocouples are usually quite confusing in school. Me personally, when I was taught about thermocouples in school, I never knew what the teacher was talking about. And to me, it was just like, oh shit, what's this talking about? I don't even know what's this thing here. Now, if you want to understand what a thermocouple is, you just have to understand that it's basically a overpowered thermometer, right? So if we were to put it in layman terms, it's basically like a thermometer. It's like a thermometer on steroids. Why do I say it's like on steroids? It's because these thermocouples have two main advantages. Number one, it has like ridiculously large range. The range is anywhere from negative 200 degrees Celsius to 1100 degrees Celsius here. Something that no thermometer can definitely do, right? If you ever find a thermometer that can measure this range, please let me know. I would like to buy it as well. And the second most important thing about a thermocouple is that it has ridiculously fast responsiveness. Why does it have such a fast responsiveness? It's because it measures change in temperature with metals instead. Guys, like I mentioned, thermometers, right? You can only measure temperature change when the heat reaches the liquid and expand the liquid slowly, right? For thermocouples, you don't need that because it is made of metals, okay? Now, once you understand the advantages, you need to know what a thermocouple is made of. It's in the next page, by the way. It's on the top there. Yeah. So a thermocouple is made of like 3 to 4 main components. The first major component, pay attention to this, guys, it's important. The first major component is something known as a galvanometer. Probably none of you guys have heard of a galvanometer before. Do you know what a galvanometer is? Yes, as usual, right? Galvanometers will usually be something you learn in your year 11. And in this particular part for me, right? Galvanometers are basically things that can measure very, very small change in voltage and amperes. If you want to put it in layman terms, right, you can just like imagine like a millivoltmeter, kind of married like a milliammeter. And then they gave birth to a galvanometer, right? This galvanometer can read two things, either very small changes in voltage or very small changes in amperes, guys. So this is what a galvanometer is. It's a very sensitive voltmeter and ammeter, essentially, right? So it's combined together to become one thing. Okay, so once you understand what a galvanometer is already, right, the next part which a thermocouple is made of is basically a different type of metal, right? Let's imagine this blue color wire here is copper. Okay, let's say it's copper. It doesn't have to be copper, but for this example, let's just say it's copper. This copper will be connected to two specific junctions. Number one, it is a junction known as the cold junction. Number two, it is a junction known as the hot junction here. Okay, cold junction and hot junctions are basically any temperature range, but later on we're going to calibrate it first. But just keep that in mind first. It's going to be connected to a cold junction and a hot junction. Then after that, it will be connected to a different metal here, okay? Let's imagine if the blue color metal is a copper, right? This purple color metal will be some other metal. It can be any metal but copper. It can be steel, iron, tungsten, bronze, whatever metal it is, right? It doesn't really matter, but the conclusion, it must be a different metal. For this case here, let's just say it's made of iron, okay? Now, this thermocouple is made of these things here. But in order for me to use a thermocouple, like a thermometer, first and foremost, we must calibrate it. And like I mentioned just now, in order to calibrate it, what are the two temperatures that we use again? Good, excellent. We are going to use 0 and 100 degrees Celsius. So let's say as the cold junction, we're going to put melting ice into it, like we put a cup of melting ice into it. And at the hot junction, obviously 100 degrees Celsius, right? It means to say we're going to put 100 degrees Celsius of boiling water. So you can kind of imagine these two wires are poked into the melting ice and another part is poked into the hot junction, guys. So you can anytime lift it up and put it into another cold junction or lift it up and put it in a different cold hot junction. But for the sake of understanding right now, in terms of calibration, let's say we placed it in 0 degrees Celsius and 100 degrees Celsius. As soon as we place these two things into the two different temperatures, right, what's going to happen is this galvanometer is going to give me a reading. Okay, let's say this galvanometer gives me a reading of 0.1 amperes. From here, this is going to be your baseline, guys. Your baseline understanding is that every 100 degrees Celsius change in temperature, the galvanometer will read 0.1 amperes. It doesn't necessarily have to be 0.1, but now I'm saying, let's say it's 0.1. Usually the question will give you all this information. But now let's say it's 0.1. From here, once I have calibrated the thermocouple, Okay, good. I can measure super hot stuff and I can measure super cold stuff already. Let's say right now I want to measure something that is super damn hot. I don't know how hot it is, but let's say it's pretty damn hot, right? And then of course, I'll still remain the cold junction at 0 degrees Celsius because I can only have one variable that is changing, right? I don't want to change both things, right? If not, I will know where's my point of reference. Let's say right now, when I put the thing at a super hot, the two copper and iron metal into the hot junction, and I put back the other two sides into the cold junction, which is 0 degrees Celsius, this galvanometer right now gives me a reading of 0.5 amperes. Now, logically speaking, how hot do you think the hot junction is at this point here? Good, excellent. It is going to be 500 degrees Celsius. Why? Because just now we calibrated, right? Just now we calibrated that every 100 degrees Celsius difference, it will give me 0.1 ampere reading. If today I'm measuring something that's super damn hot, and then I'm using the same cold junction, if it gives me 0.5 degrees Celsius, it tells me that the difference is going to be 500 degrees, right? And if it is 500 degrees, then of course the hot junction is at 500 degrees Celsius. Before I proceed on, anyone don't know what I'm talking about? This is quite important, guys. Anyone need me to repeat this or not? 100% absorption rate from online as well, just what I like. So if everyone understands what I'm talking about, let's say right now I want to measure something that's damn cold, right? Right now I want to measure something that's damn cold. So obviously what's going to happen is I'm going to place back the hot junction to 100 degrees Celsius, right? Right now, this something is damn cold. I don't know what's the temperature, but I know that when I place it in the very cold temperature, the galvanometer gives me a reading of 0.3 amperes. Everyone PM me your answer. What is the cold temperature here? Everyone PM me. What do you think? Sorry? Definitely. Use the calibration part again. If it's 3 degrees, then how can the difference be? If you refer it back to the first one and the last one, how can it be 0.3 amperes? Negative how much? No. You're a bit confused, I can tell from your answer. You try to refer the first two and then look back at the last one. The tip here, guys, is that the galvanometer reading gives a difference in the temperature from the known temperature, guys. I repeat, the tip here when you're doing the calculation is that the galvanometer gives a reading for a difference in the temperature. It's supposed to be a difference in temperature. 2 degrees Celsius is not correct. Refer to the first two samples here, then try to think about it very logically on your third answer here. Okay, everyone, you're supposed to PM me your answers, by the way. I don't know. Jihin, do you not understand the first two? Look at the first two examples and tell me what the third one should be. Zero, your head, zero. If it's 0, then wouldn't it be the same as the first one? I know. Here is 0.1, here is 0.3. How can here be 0? Minus 0.3. That's wrong as well. Come on, someone give me the right answer. The answer is a negative answer, by the way. Negative 30. Yeah. Nope, that's wrong. How do you get negative 30, by the way? What was your reasoning? Was it wow guess? Okay, bloody hell, everyone tell me 100% absorption rate, no one can tell me the answer. The answer is negative 200 degrees Celsius. Why? Work your way back up. Someone tell me why it's negative 200 degrees Celsius. Anyone can tell me why it's negative 200 degrees Celsius? Wow, GG. Everyone, you don't understand, is it? You know why it's negative 200 degrees Celsius now? Because, like I keep saying, right, the galvanometer is supposed to give you a reference point. No. By the way, 100 minus negative 200 will be 300. But maybe you're on the right path, Raj. But anyways, everyone pay attention. Look at this first reference point here, which I've given you guys. I said that every 0.1 degrees, sorry, every 0.1 amperes reading from the galvanometer gives me a difference of 100 degrees Celsius, meaning to say at 0.1 amperes is going to give me 100 degrees Celsius in difference. Now, if you look at the second part here, the reason why it is 0.5 amperes, right, is because the difference in temperature is 500 degrees Celsius, right? Finally, when it is at 0.3 amperes here, 0.3 amperes should give me a difference in reading, a difference in temperature of 300 degrees Celsius, right? If my first reference point is at 100 degrees Celsius here, then naturally from here to here should be a difference of 300 degrees Celsius, right? Which is essentially going to be negative 200 degrees Celsius here. Do you guys understand what I'm talking about? Anyone don't understand?
I still don't understand.
Let me explain again. Okay, everyone pay attention here. So everyone understand this calibration process, right? This calibration process here is to tell me that every 0.1 amperes difference gives me a reading of difference of 100 degrees Celsius from the cold to the hot junction. The difference is 100 degrees Celsius. It doesn't matter where I start or where I end. I know that from the hot to cold junction, every 0.1 amperes is going to be 100 degrees Celsius. Okay. Then looking at the second example here, this galvanometer gives me 0.5 amperes. 0.5 amperes means to say the difference in temperature should be 500, right? Since my starting point was 0, from 0 to 500 easy, it's just 500 degrees Celsius, right? But when I give you a trickier question, which is something like this, I say that this is my starting point. Is the hot junction is for sure known temperature because I'm measuring something that is damn cold. The starting point is at 100 degrees Celsius. When my galvanometer gives me 0.3 amperes, it means to say from the start to the end, the difference should be negative 300 degrees Celsius, right? And from here, 100 minus 300 is going to give me negative 200 here. It's all with reference to understanding that the galvanometer tells me how much is the range of each of the temperature only. Do you guys understand what I'm talking about?
Still no.
What, Chi-Hin? What do you say?
Still don't understand.
Or your line is very bad. Like, can you type? I cannot hear anything you say. Still don't understand? Nani? Which part don't you understand, Chi-Hin? Which part are you missing out? The last part here. Okay, let me give you an easier one right now. If let's say, right, I give you an easier one right now. Let's say the hot junction right now I might put at 0 degrees Celsius. Okay, the hot junction I put at 0 degrees Celsius. Then right now, this ammeter reading, right, it gives me 0.2 amperes. Okay, if let's say the ammeter reading gives me 0.2 amperes, I know that this 0.2 means to say from here to here, the difference must be 200 degrees Celsius, right? If let's say it starts with 0, then here is for sure negative 200 degrees Celsius, right? Because the ammeter reading gives me a difference from the reference point to the finding point here. You get what I mean? So if let's say later on I wanna try to be funny, right? After I've done this calibration process, I know that the galvanometer gives me readings of difference, right? Let's say right now I want to start not from 100 degrees Celsius. Let's say I want to start at 50 degrees Celsius here. Right? If let's say, right, the galvanometer gives me 0.1 ampere reading, 0.1 means to say it's 100 degrees Celsius difference, right? Means to say at the cold junction is going to be negative 50 degrees Celsius, because 0.1 is 100 degrees Celsius difference, right? From this calibration process here, I know that 0.1 is 100 degrees Celsius difference, so here to here for sure is negative 50. You get what I mean? Okay, anyone don't understand? So far, I've given you quite a few examples already. Everyone understand? I want everyone to send me the damn answer. I'm going to give you one more question here. Okay, right now, my let's say my cold junction is at negative 100 degrees Celsius. Okay, my galvanometer gives me right now 0.25 amperes. Tell me what the hot junction is. These are your reference points. Tell me what the hot junction is. Everyone send me an answer. Good. Excellent. Good. Excellent. Jihin and Jaden got the answer already. Good, Raj. That's the correct answer. Good, excellent. That is the correct answer as well. And for the rest of you guys, Leha and Nadia, what's the answer? Oh, 350. That's wrong. It's not going to be 350, right? The difference is only 250 degrees only. Well, how will it reach to 350? It's negative 100 plus 250, right? You get it, Nadia? Yeah. Wait, Leha, you understand or Leha? Leha, are you there? AFK. Okay, so this is the answers. These are the things that you're supposed to know, guys. Yeah, super important. It came out in last year, guys. Last year in your IGCSE, they came out one question asking about the calculation. Never in the history of IGCSEs have they ever asked about the calculation for a thermocouple. Last year they came out, so naturally those who paid attention answered properly, and those who did not understand. Okay, but essentially that's the things you need to know. All right, if you look back at the notes here, then right now the whole thing will make more sense, right? A thermocouple probe contains two different metals to form two different junctions. If you look at the drawing here, guys, this here says is copper and this says here is iron, right? Two junctions at two different metals will be connected to two hot and cold spots. If here is iron, then here must be copper. If here is steel, then here must be iron. If here is copper, then here must be something else. The most important thing is the top part must be different metal from the bottom part. Super important, always comes out in your IGCSEs, right? And of course, the temperature difference causes a tiny voltage or ammeter, which makes a current flow. A greater temperature gives a greater current, right? Like just now, the greater difference in temperature gives a larger reading in the galvanometer. Thermocouples are used for high temperatures which change rapidly and have a large range of -200 to 110 degrees Celsius. Sorry, 1,000 and 100 degrees Celsius here. In your IGCSEs, if they ever ask, which is very commonly asked, I've at least seen 4 or 5 of them ask this before, they'll ask you what's the main advantage of a thermocouple, and usually they'll ask you to write 2. If they ask you to write 2, the first main advantage is that it has super large range. You can keep thinking that it is a thermometer with steroids, right? And then it can respond very rapidly because they use metals instead of liquid. Guys, metals will heat up much faster compared to liquids. That's why it has a very high responsive rate, guys. Everyone understand what I'm talking about? If everyone understands what I'm talking about, let me give you guys some Google Sheet questions here. I'll send it to the Zoom link. Oh, give me a phone number, by the way. I send you some work. Oh, yeah, Hui Fong should join next week. Yeah. What's your phone number, by the way? Yeah, just give me a phone number. Type it in here. Guys, do the Google Sheet questions, guys. Can you spell your name as well? You receive it? Yeah. What is the first question? What does it mean? Okay, give me a minute. Let me change the sharing screen thing first. Duplicate, keep changes, screen here. This thing is so annoying. By the way, everyone, please do 2.2.1 first, guys. Don't do the other one first. First question, what do they want from you? Is this the one they're asking? Above that? What? What do you mean? This one? Your name? Nani? You confused. Just put down your name so I know who's writing what answer. What do you mean you have a different form? Click the first link, dude. You're supposed to see this first 2.2.1. Do you see this one? 2.2.1? Simran? Yeah. Why do you have a different form, Jaden? Oh, no. It's 4 forms, guys. Yeah. Oh yeah, by the way, guys, before class ends today, most likely we're going to spend the next 10 minutes doing these Google Sheet questions. Guys, homework, you see the notebook for the chapter after. Let me just show you guys. Wait, it's here. Hey, everyone. Oh, nice. Keep a book something. Is it the internet? The internet. Anyways, guys, before the internet breaks, I don't know if this guy dropped more than or what. Is everyone still here, by the way? Yeah, homework, everyone. Every one of these questions here, finish all the way until this page. Finish until this page here. Next week, we'll go through discussion, and if I feel that everyone is okay, we will either proceed to the next chapter or we'll spend 1 more week doing exercises on this chapter here, guys. Finish until this page here. For you, you just need to finish everything from paper because you don't have the booklet yet. And the Google Sheet questions as well. So 2 sets of homework. The Google Sheet questions, at least I can see what's going on. But usually, you know, you guys always never do the homework. So you guys are assholes. Hey, do the homework. So small. Oh, cool. Can I use my computer? Measure. Don't be shy. Maybe you want to use a horizontal, then it will be better.
It's not that small.
Really? Maybe it's because I'm getting old. Ah, excellent job. Is this you, Rupsi? Huh? Yeah or no? This one? Unknown user 111 anonymous. Right.
You guys have.
Sorry? Wi-Fi? Yeah, we do. Do you need it? But you can only use it for work purposes, yeah. It's not the bandwidth is going to be shared for everyone. Is your internet speed not good?
This is.
Yeah, I mean, excellent, Raj. 5 out of 5. Who else? Who else is doing this? Ah, Chi-Hin as well.
So I got the second question correct, but I'm not sure why.
Huh? Second question. This one?
Yeah.
Students wishes to check the upper and lower fixed points of a Celsius scale. She has 4 beakers, P, Q, R, and S. Upper and lower fixed points, which is 0 and 100 degrees. So you need to use which one that is 0 and 100 degrees. The answer was Q and S contains a mixture of ice and water. Okay, because ice and water means to say it's melting already, right? And then S was containing boiling water. This is for sure 100 degrees Celsius. You for sure won't use P and R because there's salt in it. When there is salt in it, there's impurities which will affect the boiling point and the freezing point, right?
Oh, yeah, I now understand.
So yeah, it's a mixture of ice and water, meaning to say the ice is melting. You can kind of imagine it that way. Oh, no. They are not mixing together. It's like a mixture. That's both there. Oh, Simran, this is you. 3 out of 5. Yeah, not too bad. Seeing that how you just joined today. Oh, by the way, when you click your answers, do you see that there's feedback at the bottom here?
Yeah.
It's supposed to help you understand what went wrong. Yeah. So please read through it. Okay, guys, one more thing before you guys go. I want to mention this way. Please make sure that you do the homework for the Google Sheet questions here. These Google Sheet questions are supposed to help you understand, guys. If you can understand what went wrong in these ABC questions, it will usually be much easier for you to tackle paper 4 questions. But I noticed that a lot of you guys always never do the homework, guys. This is for your sake, not mine. It's for you, not me. It's for you, not me. Please help me, help you, help me, help you. Just do the homework and you are supposed to glide past physics easily, guys. If you don't do the homework, may Jesus be by your side. Okay, so yeah, I think we'll end class here today. Like I keep emphasizing, please make sure to do all the questions, right? For those who have not received the link, let me send it to the WhatsApp link as well in the group so that you can all access it. Please, at least, if you don't want to do the paper 4 questions, at least do the Google Sheet questions. Then at least I can see how well or how unwell you understand or don't understand the chapter, guys. So yeah, please make sure to do the homework. Simran. All right, yeah, we'll end class here today. If you have any questions, you're welcome to stay back. If not, we'll continue this next week, guys.
For the 2.2.2,
2.2.2. Bye-bye.
the 4th question, what does it mean by the ball?
4th question, let me check here. Which factors affect the sensitivity of a thermometer? So sensitivity is only affected by 2 things, right? Either the diameter of the ball, which is obviously this one here, and no thickness, no length. Length affects the range, thickness affects the responsiveness. So only A is the answer. Why?
No, what's the meaning of the ball?
What?
What's ball?
Ball. Okay, the ball is basically like the hole, whenever you say ball is considered a hole, so like the diameter of the ball, they're actually talking about diameter of the capillary tube where the liquid passes through the thermometer. You understand what I'm talking about?
No.
Okay, just in conclusion, a ball, right, is just a hole which is also representing the diameter, the capillary tube of the thermometer.
So the ball and the bulb is different?
No, the ball of the tube. So it's the hole in the tube. If I were to draw it, it's going to be something like this here. It's like, this is the tube, right? The hole inside this is called the ball, which is essentially the diameter of the tube. Understand?
Oh, yeah.
Yeah. So this is what you're supposed to interpret from that. Okay. Yeah, you can leave already, guys, for those who have no questions.
Thanks.
All right, bye-bye. Make sure to do homework.
Yeah.
Okay, welcome.
Thanks. See you later.